Okay, hey everyone, and it's a pleasure to have with us today Amir Dembo from Stanford, who will tell us about averaging principle and the shape theorem for growth with memory. So, Amir, please.
Yes, so it's a pleasure to give a talk at the University of British Columbia Probability Seminar, and I will talk on a joint work with Rujun Huang, Pablo Groisman, and Vlada Sidorovicius. This paper just appeared and is devoted in memory of Vladas, who unfortunately passed away recently after the paper was written. Okay, so, now again, I cannot do this. Just a minute. Okay. So I will start by talking about a general family of growth models, Laplacian growth and motion models in random media. And random growth processes arise in many physical and biological phenomena. They go back to the Eden model or first passage percolation in the 60s. And there is much challenge to understand the revolution and the formation of macroscopic pattern out of microscopic rules of motion. And in particular, what I will discuss here will be a family of growth, members of family of growth models called Laplacian growth models. And those are models where the growth at each portion of the boundary is determined by the harmonic measure of the boundary from a source. This will not be exactly what I will do, but it's a motivation for that. And examples of such models, well-known examples is diffusion limited aggregation, or DLA, from dating back to Witten and Sander work in 1981. And there is a huge arsenal of a huge collection of papers in the physics literature about DLA with very limited amount of mathematical knowledge about this process. A much easier process is a so-called internal DLA, or internal diffusion limited aggregation, which appeared first in McKean and Deutsch in '86, and later in the mathematical community by Diaconis and Fulton in '91. And this is a model which I will explain in a minute. And this is much easier because the motion, the growth, the particles, the source is coming from the inside, which tends to smooth the pattern, as opposed to the DLA, where the particles, the source patterns come from the outside, which tend to develop a more fractal shape and therefore much harder to analyze. More related and motivating this particular work are two related models of motion in random media. One is a once reinforced random walk, or I will use a notation ORRW, coined models proposed by Davis in 1990. And the other one is origin excited random walk, or ORW, which was a model which was proposed by Kozma in 2006. And I will go over the formal description of the last three, the IDLA, the ORRW, and the OERW in the next slide. So let's start with the IDLA and look at what kind of shape theorems one can prove in this context. So the internal DLA model, what one does is at each step, you run a simple random walk in Zn, and the simple random walk, the particle is running until it exits a current range. You start with a range, maybe starting with a point or some other initial source, and you start a simple random walk, let's say in the origin for a moment, and the particle runs until it exits, gets to a place which was not visited before by any of the former particles you visited, at which point you add the point, the position from which the particle exits the range, add it to the range. Now the range grows by one step. You increase the step by one, and a new particle moves to the origin and starts the walk. So every step of the walk is adding 1 point to the existing range. And you are interested in the growth of this range, this random subset of Zn. In a paper which is well known of Lawler, Bramson, and Griffiths from 1992, shortly after the introduction of this model by, or the popularization of this model by Diaconis and Fulton, for a point source, that is the example I mentioned, where the particles keep running starting at the origin, Lawler et al. Proved that there is a shape theorem which is a ball. What does it mean? It means that for every eta positive, almost surely if T is large, the range suitably scaled to have a volume approximately 1 is contained, or volume approximately that of a ball of unit of radius T, is going to be contained in a ball of radius 1 minus eta T and included in a ball of radius 1 plus eta T. Doesn't mean that the range is a random set, and the boundary of the range may be quite rough, but it is contained between two balls. So if you will normalize it, scale everything down, scale the lattice, what you will see is the emergence of a nice smooth ball-like shape in the limit. This prompted interest in generalization of this model in various directions, and I will describe below three generalizations for which mathematical analysis was possible. The first one was done by Gravner and Quastel in 2000. They looked at more than one point source. So the point sources are distributed in the space, in the plane, or in Zn in some places, fixed places. And then what they did, they ran particles in parallel. They emit particles at Poisson rate epsilon to the -1. So at a high rate, they emit particles from all those sources. And they look at the empirical density on a rescaled lattice. And they show that it converges weakly as epsilon goes to 0 to a solution of a Stefan free boundary problem. What does it mean? Let's kind of phrase what it means, rephrase what it means in terms of the Lawler et al. Theorem. What happened is that since you are running the particles at a fast rate and rescaling the lattice, you lose a discrete geometry, and more or less you can think of yourself, at least intuitively, as running a cloud of Brownian motions starting at these fixed points. And what you will see, the empirical density will converge in the domain which is reachable by the particles. It will converge to the solution of the Laplacian, of the heat equation, which represents the average behavior of a Brownian particle. But this solution of the heat equation will only be valid in a domain which is a domain on which the particle reach. And the support of this domain is going to be the analog of the shape theorem in Lawler et al. And what you will see this support growing in time. And outside the support, the solution is of course 0 because no particle arrived. And the boundary of the support, this is why it's called the Stefan free boundary problem, the boundary of the support is growing by the flux of the particles coming from inside. So you have a boundary condition that the derivative or the gradient of the solution of the heat equation is going to be acting on the boundary, and that's the way that the boundary will grow in time. Another work by Levine and Perez 10 years later took a different point of view, again looking at general initial conditions, and again looking, say, at the IDLA I described, but now the particles are they are now running sequentially and discretely, like in the work of Lawler, Bramson, and Griffiths, but the particles now can start from more general initial conditions, maybe points, maybe even within a sets. And what you do, you still increase the sets randomly, but you may have 2-3 different clouds of particles, and they each grow according to an IDLA until they combine together, and then they grow together. And they again proved a result for an explicit limit shape. They wrote the limit shape in terms of a variational problem. The variational problem will give rise to a ball if the initial condition is a point. But if you start at 2 points and you grow 2 balls, for example, and when they emerge, you get some kind of ellipse, or ellipsoid, which kind of grow in a more complicated way. They in this paper of Levine and Perez, they also analyze other models, not necessarily the IDLA, other models like rotor aggregation and abelian sand piles. what is common to all the models, and that's why the success of this paper of Levine and Perez, is that those models, same as the IDLA, have this abelian symmetry. Even though it may seem like it matters what was the order in which the particles moved, in the models of Levine and Perez, the same as in the IDLA, actually the specific motion of the different particles, the order in which you send them, is irrelevant as far as you are concerned, for example, with the range after time t. And that gives you a lot of room in the mathematical analysis. The first paper, the paper of Gravner and Quastel, in contrast, rely on hydrodynamic limit, on the fact that you are having all these particles moving by Poisson process at the same time, give you a lot of independence and again, exchangeability, which help in the analysis. The first paper in 2017 was the first paper in this, the first and the only paper in this topic, which analyzed a model with memory. And that is a uniform IDLA. What is the difference here? You run exactly the same IDLA as before with a simple random walk, but only the first particle start at the origin. What happened afterwards, upon exiting the range, the next particle will start at a uniformly chosen point within the current domain. And this gives rise to a loss of the abelian symmetry, the loss of this exchangeability with respect to the order of the particles. Nevertheless, because of the uniformity of the initial conditions, you can think of, imagine, for example, that R was already a ball. If R was already a ball, then the new particle will start at a position which is rotationally symmetric, because it's uniform in a ball, and therefore there is no reason that the limiting shape will not change to a ball. The paper by Benjamini et al. Is actually doing the harder work of proving what I just told you, which is a non-trivial task. Okay. In a different direction, there have been the models I mentioned to you from random walk in random media, and I will describe two models here: the excited walk towards the center and the special case of origin once reinforced random walk. So excited random walk is a collection of models proposed by Benjamini and Wilson in 2003, and analyzed, some of them were analyzed nicely by Kosygina and Zerner in 2013, and there have been more analysis of these models. What these models are, it's models where you run a random walk, you run a simple random walk, except that at the first visit of the random walk to a given vertex, it gets a one-time drift in a fixed location direction. For example, in the coordinate, positive coordinate of the first direction, E1 or X direction. Subsequent visits to the vertex, you perform a simple random walk. So what happens here, if you think about it, after some time, you have the domain of all the vertices you have already visited, the range, and inside the range, you perform a simple random walk. Outside the range, once you go outside the range, you get a drift to go out. So it encourages you to go out in a particular direction. In this model, unlike the previous model, we have only a single particle. We have just a single particle performing a simple random walk whenever it's in the range it visited, and having this change of rule at the boundary. This is a simplified model of once reinforced random walk, where the drift direction is not fixed. In a once reinforced random walk, what you have either a model with edge conductance or model with vertex conductance. It's a conductance model, which is a symmetric conductance model with a constant on ZD with a constant conductances will just be a simple random walk. But what you are doing again on the first vertex, on the first visit, to an edge or a vertex, the conductance is 1. And after you visit it, this conductance is moving 1 to 1 plus A. A is positive. So what it does, it encourages you to visit, to go back to the places you have visited, because the edges or the vertices you have visited get a higher conductance than the one you do not visit. So it tries to keep you more confined. Kozma in 2006 studied the origin origin excited random walk, which you can think of as a case of a excited random walk, where the drift now is going in the direction connecting your position to the origin. So what does it mean? The first time you visit a particular vertex in Zn, what you find is that instead of having a simple random walk, which is what you will have in the other visited, where you have all 2n vertices next to you are going to be of equal probability, in the first visit, you rearrange the probabilities in a manner which will put a drift back towards the origin, just a drift along the line connecting the vertex V to the origin. So you rearrange the probabilities in such a way that you go radially, on the average, you go radially back a little bit to the origin with a weight delta which is positive. And what Kozma proved, which was quite maybe somewhat counterintuitive at first, that even if you take higher dimension, if you take dimension bigger than 3, where the random walk is transient, and any delta positive that you can put will be sufficient to make this object recurrent. So this small drift backward is enough to make the object recurrent, even though as time goes on, you visited more and more points, and therefore you will reach the boundary more and more less and less often, so you actually get the drift quite infrequently, but it's sufficient to make you recurrent. Kozma, in follow-up 2 papers in 2007 and 2013, conjectured that you should have a shape theorem for most origin-excited random walk. He did not make precise what most is, but the point is that you can change this rule a little bit, not go radially, but go in a different manner. And the claim is that this origin-excited random walk drift backward will make it into a recurrent object and will also create the emergence of a smooth limiting shape like in IDLA. Maybe not a ball, but something smooth and macroscopic. Sidorovicius made the same conjecture at about the same time for the origin, for the once reinforced random walk, if the reinforcement strength is large enough. If the reinforcement strength is small enough, simulations show that you do not get a limiting shape. But if the reinforcement is large enough, it kind of keeps you more confined and create a limiting shape. And the principle here is that the connection between the recurrence proof of Kozma and the existence of limiting shape is that if you pretend or believe that there appear a bulky limited shape, like in the IDLA, then you can actually use it to prove the conjectural recurrence of such random walk. Because what you will do, you will be confined, but you will not be too trapped within a small region. Because you have a limiting shape, you will not get into a fractal-like or one-dimensional-like shape that will keep you far away from the origin. And the shape, if you have a shape theorem, you can conclude that if you are walking ideally in a ball, for example, you can easily calculate the excursion probability, the probability that you will get back to the origin before you get to a new point, and you can deduce recurrence out of this. So one way to prove the result of Kozma is to prove a shape theorem first. However, this method or this approach seemed to be much harder, so Kozma in the proof of recurrence for this particular model actually goes around about in a way that he avoids ever discussing a shape theorem. So he conjectures that it exists, but he cannot really get a mathematical handle on it for reasons that I will explain in a minute. So here are some simulations to indicate what happened for these models. So this is a simulation that we did on vertex once reinforced random walk in 2 dimensions. All the simulations are in 2 dimensions, so it's possible to view them. The reinforcement strength is changing from the left, middle, and the right. So the right one is the one where the reinforcement is really high, whereas in the left and in the middle, they are kind of small. And we are running the simulation obviously on a finite box, but the box is of large enough size that you will not really reach the boundary of the box. And the color is proportional to the to the square root of the first visit time. So different colors will represent for you the boundary of the shape theorem at increasing times. And you see that in the right picture, it looks maybe not a ball, but it looks pretty smooth limiting shape, whereas in the left one, it's kind of probably fractal-like and not having a limiting shape. So this is kind of along the lines of Sirovicius' conjecture. Any questions?
Sorry, so is there really convincing numerical evidence that this persists also for much larger times, that it doesn't just require a lot more time to become smooth with, say, a=2?
I think we ran simulations even longer, and other people ran simulations quite long. I don't think it gets smooth, but I don't know of a convincing, really extremely long simulation. So I don't know. And there is no mathematical analysis of any of these things. So we don't have any evidence other than simulation. Okay, this is another simulation of another model. Now this is simulation of the origin excited random walk on Z2 with different excitation rules. And the difference here is how do you arrange the drift when you get to the boundary? On the left, what you do, you go in a coordinate chosen with probability proportional to the absolute value. You have here two coordinates, and what you do, you try to go back when you are at the boundary, you have two, when you say here, you have two possibility to go to the, or three possibility to go to the boundary, and what you do, you go back one unit towards origin in a coordinate, either x or y, are chosen according to the absolute value. So if you are here, you will probably, if you are here, you will probably go in the x because the y is 0. If you are here, you will go down with the y because the x is 0. And here on the boundary, you may go 50-50, choose to go either x or y. In the middle, you will go always in the direction of the coordinate with the largest absolute value. So your movement on the boundary will be down here, up here, to the right here, and to the left in this direction. And on the right, sorry, I was confusing. This is no, on the right, you go down to the origin in both coordinates, right? So you always go here in a 45 degrees, right? So you go back in both that way and that way. And you can see that there is a shape theorem. It looks like there is a shape theorem, and the shape is different, reflecting the choice of your excitation rule. So for example, in the case where you go in both coordinates, you derive an L1 ball, which is kind of similar to what you are doing. You go in a 45-degree boundaries. Whereas here, when you choose to go up or down with one coordinate, you get probably a square at the end. And here you get a shape which is more complicated. And since we don't know how to prove anything, we don't know what it will be exactly. But this is also supporting the conjecture of Cosma. The different rules of excitation will still give you different, but will still give you shape theorems. Now, we cannot really analyze these models. So instead, what we did, we derived a much simpler model, or simpler model for analysis, which captures some of the essential points, essential properties of these discrete models. And we ran simulation on it to see that it's actually having very nice numerical result, and then we can actually prove mathematical theorems about it. So the remainder of the talk will be about this simplified model, random growth model on Rn. So first we get rid of the lattice geometry, we work in continuous, and then we simplify somewhat also the rules of the model. So here is the way the model is run. So we construct a growth model in Rn to bypass some of the technical difficulties of lattice models. So what we are interested in is in a family of domain processes, right? This DT, they will capture what we expect to be what the object to which we want to show a shape theorem. And it has a scale and Poisson rate parameter epsilon, similar to what we did earlier on with the IDLA, or also with the simulation I showed you for the lattice models. We always keep the particles running faster or increase time at a rate epsilon to the -1 and rescale space at a rate epsilon. So that will be this small epsilon. Now, our rules are simplified in the sense that they keep the domains star-shaped and compact. So we do not let the domain develop a hole inside that will make it complicated. And because of that, we can represent our domain by a boundary function, a function which is on the sphere to r plus, telling us for every angle what is a radius, how much did we advance in this particular angle. And the way we run it, what happened, I'm proceeding with the mathematics, what happened is that this object, this boundary, is a slow process. It's a pure jump process. It's always gaining, like in the models of all the models I described, IDLA and origin reinforced and once reinforced random walk and origin excited random walk. There are always the boundaries, the range is only going up, and but it's going up slowly because at every time you only add 1 point in the discrete motion, which means that in principle you add something of volume epsilon. So we are also adding a small bumps of approximate volume epsilon at a random point on the boundary. That is this family of models. Now, how do we add it? We derive the growth by a fast particle process, xt of epsilon, and xt of epsilon has a heating probability density on the boundary of the sphere, which depends on the angle. It's a density of the angle, but it depends on two things. It depends on what is the range, because you are only going to heat it according to the shape you have already, and it also depends on where the particle starts. And we want to model in some sense the models of once reinforced random walk or origin excited random walk. So we don't want to start back at the origin like in the IDLA. So we have one rule, which is a density given a shape, a point, and an angle. And this specifies the law of the angle where the bump is going to be added. And then we have another map, H, which given the boundary, given the point we just hit the boundary and the domain in this time, transports the particle back upon hitting the boundary at angle psi of t. So f, to recap, f is a function. These are two deterministic functions. And together they will determine how the model evolves. So the deterministic function f is acting on functions. We want them to be continuous, on continuous positive function representing the polar representation of the radius of our domain times a position x, which is going to be a position within, enclosed between the shape which is encompassed inside R, and it sends us to another density, which I hopefully also continues, again on the boundary of the circle. So for example, if you imagine running a Brownian particle starting at x within the shape R, then frx dot will be the Poisson kernel associated with the function R. R is telling you a function. You can calculate the Poisson kernel starting at a point x, where what is the probability that a Brownian motion will hit the boundary of her shape at a particular angle. And the function h is again a function from a set R, which is constant, and an angle z, going back to the whole space. And then one example is to go back by a fraction alpha. You just go, that's the analog of Kozma's origin excited random walk. You go back vertically. So if you were hitting at angle z at radius r of z, your next point you will go will be alpha times this number, where alpha is strictly less than 1. So you go back by a fraction alpha, which may be close to 1 but fixed, and then you start your new motion. Any question on this model, at least on the rules and how we are trying to connect to the previous models?
So F gives you some random location where you will add some bump, but H is assumed to be deterministic.
And H is
there's no randomness in H.
You can also randomize H, but we did not see a need for that. But it will not change that much. I mean, H.
I mean, you can incorporate that into F in the next step.
Sorry, F is really also deterministic, but F represents a distribution. Here H represents a deterministic map, but in principle you could have made H RZ not going from C times S to R, to go from C times S to a, if you want a distribution of points, and you will choose the next X, not deterministically, but you will choose the next X randomly given this angle. I think that's what you mentioned, Omer. You can make it a more general model. We did not try to do that because there was enough work to do already, but this is not the essential point. The essential point, I can even tell you what the essential point is. The essential point is this alpha in my example, meaning the essential point that we actually go back macroscopic distance from the boundary. And that is the main difference between these models and the previous models which I mentioned, because when you run a simple random walk or a random walk to the range and you have something happening at the boundary, the next step is typically one step from the boundary. So it's really very close to the boundary. And the main problem is that the boundary of the domain, even if you expect to have a shape theorem, the boundary of the domain is not going to be smooth. It's going to always show some factor percolation. Even in IDLA, there are results about how the boundary looks. And if you magnify your simulation, you see that at the boundary is very rough. And the fact that the boundary is very rough can pose a lot of trouble in the sense that you can be getting stuck at local microscopic configurations which are very strange, and you really cannot analyze the motion for that reason. By going back even 1 minus delta, but delta does not depend on epsilon, we kind of entangle the roughness of the boundary with the motion of the particle. And that is key to the success of the mathematical analysis. So we can make H to be giving you a random distribution as long as you are not going to stay at the boundary with a high probability or a distance much. If you want, we can even probably improve it, but we need to go back a distance which is not epsilon, which is much bigger than epsilon away from the boundary. So here is more on the details. How do we add a small bump on the sphere? What we do, we essentially add, we have a function, right? We have a shape. And what we do, the way we add the bump is we decide on the center of the bump. And then what we do, we add, here is this picture. You have a ball and you want to add a small bump here. So what you do, you look at the inner product between your angle and the center, that is kind of the distance on the sphere, and you add a small function, and this small function is arranged in such a way that it will be 1 at 0, or it will be 1 or very high at the center when the inner product is 1, and it drops down quite quickly. So the support will be very small. So what you want by a small bump, you want the bump to be small both in polar coordinate, to be localized, and also of a small height. So the end result of what we do is essentially we add a bump whose height is order epsilon to the 1n, and it's supported on a spherical cup of radius 2 eta, and eta is going to be probably also about epsilon to the 1 over n in such a way that the total volume of this bump that we added to the shape is going to be of size epsilon. This is just a mathematical way of expressing doing that. And here are the details of our random growth model. So what we do is the following. We have our heating kernel and we have our transportation map. And what we are doing is as follows. We have first a rate epsilon to the 1 minus 1 Poisson process, which determines the rate in which we add stuff to the boundary. And at those arrival times, what we do, we update both the radius and the position of the new particle as follows. If given all the history up till now, what we do, we first choose an angle according to the previous position of our particle and the current shape and our density rule, right? In the example I mentioned, this is like running a Brownian particle starting at xt minus within RT minus and checking what is the probability that it hits a certain point at the boundary and choosing the angle at the boundary according to this or the point at the boundary according to this rule. Once we have done that, we update our shape. So we take the previous shape at every angle, we add to it our small bump centered at the random point we just found, and we rescale accordingly. And how do we rescale accordingly? The way we rescale is as follows. We want to make sure that the volume that we add will be approximately epsilon. But what does it mean approximately epsilon? What we do, given the history, given x and r, we can calculate what will be the f, what is the average angle that we will hit, and we can calculate what is going to be the volume. And the volume on the average is going to be epsilon to the 1 over n, which is a bump up, the eta to the n minus 1, which is a scaling on the support. And then we have a factor which comes from the effect of having not equal radius at different angles. And this we average. Instead of putting the random value, we just average it out. And we use this factor and we match it to epsilon. What it means is that on the average, if you take the expectation of this thing, this quantity, condition on RT epsilon minus and XT epsilon minus, the expectation of all this stuff, of the volume of all this stuff, is going to be exactly epsilon. And then once we are done with that, we calculate deterministically, but we could have done it randomly, the position of the next particle to start with, which is given the current angle we hit and the current shape. How do we go back? This xt epsilon is supposed to be another point, a new point inside the domain enclosed by RT of theta. So this is a rule that we do. This is a way we describe a random process. And we are interested in the limit as epsilon goes to 0. Epsilon goes to 0 means many particles are emitted and each particle adding a small bump. Any questions on this description?
How sensitive is what you are going to tell us later about the specifics of how this, on the shape of this G and how exactly the scale of this G is chosen? So
the shape of G is completely irrelevant. The scale of G is just chosen so that you add a bump of size epsilon at rate epsilon to the minus 1. If you change it to different powers, you do not have a limit. The specific constant does not really matter. We could have not normalized by this. The limiting shape will be different every time.
Yeah.
The formula for the
so if the normalization.
Sorry?
So if the normalization was done in some other way, so still that you have approximately or even exactly volume epsilon, then it will be okay.
Yeah. You will probably, under suitable condition, you need some suitable condition, which I will mention later on H and F to get the theorem. And here I'm going to say that there is a limiting shape. The limiting shape, the formula for the limiting shape will involve the choice of H, the choice of F, and the fact that we are normalized with this way. It will not involve the function G. The function G disappears completely. The particular kernel, the way you do the bump, this is completely washed out. Did I answer the question or no?
Yes, thank you.
Okay. So here are simulations of our random growth model to show you they are kind of similar to the simulation I show you about the origin excited random walk. So here in all of them, we take the harmonic measure from a particle corresponding to sending Brownian particles. So the only difference between the three is how do we choose to go back. And in all of them, we don't go back too much. We don't even go back by a fraction, but we go back by a constant, but still not epsilon, a macroscopic constant. So what we do, we keep the angle and we go back from the boundary by reducing something from our radius. So at every angle, we have a particular radius at every given time. And what we do, the next particle will be coming from exactly the same angle we hit the previous particle, but we go back. How do we go back? In the left one, we go back by 1. In the left one, which is a circle, we go back by 1. So we actually keep radial symmetry, as you can see, because you can change the angle and everything is rotationally symmetric. and the result here will be a ball. You can see in your eye that the result is kind of a ball. In the middle one, we still go back, but now depending on the angle you do, you can go back more or less. So depending on the distance between the L2 norm, this is a vector in 2 dimensions, between the L2 norm and the L infinity norm, so you go back more when you are, you go back more when you have one coordinate which is large and the other coordinate is small. So you go back more here than at 45 degrees. And the result is indeed close to a square. I don't think it is a square, but it's close to a square. We don't really know what the shapes are, except that they exist because the formula for finding the shape is to solve an infinite dimensional ODE. So we don't know how to do it except doing it also numerically. In the third one, we take a different approach of taking the L1 norm to the L2 norm. So we actually go down more on this direction and we get closer to a diamond. So you see here 3 measures or 3 limiting shapes, which kind of analogous to the simulation we ran for the origin excited random walk. And you can also see one other thing from this simulation, that in the beginning, for a very small time, macroscopic but very small time, all of them, it's hard to see, but all of them start developing, the different colors represent the shape you had at different times. So the different colors, they start all circular. So in the beginning, they all started at 0, and they all are starting like IDLA-like, because you started at the origin in the initial condition. As time becomes larger, the shape starts to fill the geometry, and the limiting shape that emerges will depend on the rule H. And you can see that you have here a sphere, something similar to square and diamond, are similar to the different excitation we did for the origin excited random walk. Now again, we chose things specifically to get shapes closer, at least intuitively, to expect shapes closer to the ones for the origin excited random walk. But this shows that this model keeps some similarity to the previous models I showed you in terms of the behavior. Okay, now what is a limiting shape? Here is, I will give you the formula for the limiting shape. The limiting shape is going to evolve according to this formula, which is written here under ODE. And I will explain how it goes. Imagine for a moment that the domain is not evolving. You just run your stuff on a frozen domain. You just don't change the boundary at all. No bumps, nothing. You just do this model that you take a particle, it hits a boundary, it gets back, it hits a boundary again, it gets back, and you record this process. This is going to be a process, xt of epsilon. Epsilon represents the rate, and it is indexed by r. Give me the domain, it's going to be a homogeneous time homogeneous Markov process in continuous time confined within R. Let's suppose that for every R, this process at rate 1, let's say, has a unique invariant law. Remember, this process, what it represents for us is the point where we started our particle. Now, if we have a unique invariant law, what we can expect as a limiting answer for our random model where R can change as follows. We can think of what we do. We simply take the derivative of R, derivative in time of our boundary, to represent the amount of flux, the average number of particles hitting this part of the boundary if the domain is fixed. So we take R at time t, and given R at time t, we calculate the flux. This is a number I call B. And this flux at angle theta is going to be the gradient of RT at time theta. So this is this, I called it an ODE because it's an ordinary differential equation per angle. It's an infinite dimensional because you go on all the angles, and they are coupled because you actually use the whole global shape to determine the value of the flux. And how do you determine the value of the flux? First of all, if a particle hit at angle theta, which happened with probability f, then the amount that you get there will be omega over, omega is just a number, it's just the spherical surface of the sphere, divided by this y. That has to do with our normalization, to the question, earlier question of Omer. If we did not divide by y in our original normalization, then the formula for B will be different. It will not have this factor y. If we divide by something else, it will have exactly the different factor. And how do we calculate the B bar? to calculate the B bar, we take this function B, which still depends on the shape R and the point X, and we say until R is changing, we must have sent many, many particles because each one of them had only volume epsilon. So effectively, heuristically at least, it looks like what we should expect is to simply integrate the flux according to the invariant law for the particle. So the particle is a fast process, the domain is a slow process, and we have a lot of particles moving so they can average, and we can think of them getting to the invariant law, even though in our model, every time the shape changes slightly. So this is a formula, and one way to see this formula also is to do the following. You can take your RT epsilon, the original model, not the frozen one, and this has a martingale decomposition because it's part of a Markov process. We have a Markov process of R and X. And in this martingale decomposition, we have a martingale part, which is not important, it's a noise. And we have a bounded variation part, a drift. And the bounded variation part is going to be exactly this quantity that I mentioned here, this B, but convolved with our small bump. When eta goes to 0, when epsilon goes to 0, our bump goes close to a delta function. And so our bounded variation term is going to converge to the flux that we see here. And the martingale term is going to have a quadratic variation of order epsilon, so it will smooth out in the limit and will disappear at the scale in which we work on. And what we also see is if we look at the Lebesgue measure, at the volume of the solution of this ordinary differential equation, it's very easy to check that the volume of this solution, the Lebesgue measure of the set enclosed by RT of theta, is going to be the volume of the initial set plus T. You get here exactly volume 1 extra, corresponding to our statement that we send particles at rate epsilon to the minus 1, and on the average add volume epsilon. So the volume grows linearly, and this, as I said, is in line with the fact that the expected value of the Lebesgue measure of the new shape given the history minus the Lebesgue measure of the previous shape is going to be epsilon at every jump. And you have approximately 1 over epsilon jumps per unit time. So here are the type of assumptions we need to make on F and H in order to prove the theorem. And the type of assumptions are as follows. First of all, what we do, we want to keep, what we need to do, we need to keep R from collapsing to 0 or going to infinity, right? We don't expect the limiting shape to be a ball, but we expect to have a limiting shape, which means that we somehow expect the maximal radius and the minimal radius to be confined. So we define a collection of points, A, collection of shapes, A, which correspond to functions on the sphere which are smooth enough, continuous, strictly positive, and having some control on a P norm. And then we are looking at extended notion. These are points and sets, point and set, such that the point and the set are in the domain of our F, right? For example, the point X should probably be inside the domain in R. The shape R stays in this original domain, and the point X should be in the image of our map H. So when we are running the process, we are always starting from an element where X is in the domain, in the image of the transportation map, and R, hopefully, we hope to keep it in this nice set and not take it go away. There's one assumption we need is a type of a Lipschitz assumption. We need some assumption saying that if you start at R and R prime, which are close to each other, shapes, and X and X prime points which are close to each other, then the result in some norm, the function F, the rule that we are using, is supposed to be Lipschitz in terms of, or have some relationship to the distance between R and R prime and X prime. And we want this to be uniform at least as long as we did not get out of this shape or this collection of shapes that we have done. And very similarly, we want the same for the rule H. So we want both our rules to keep, if you have a small perturbation, we don't want it to magnify the perturbation too much. we also want the function f as the function of the angle to be nice enough. And the nice enough, the assumption we made is bounded Lipschitz, have a norm on the bounded Lipschitz norm of the density. Now, we don't really need such strong assumption. We can get away with weaker assumptions, but the weaker assumption will be longer. So here I wrote for you simple sufficient conditions that will be good enough. And I wrote them as regular f, Lipschitz h, and Lipschitz f, kind of. And a second assumption we need was already mentioned before. We want to make sure that if R is constant, we will have a unique and exist invariant measure for our fast particle. This we need about the Markov chain. And we also need to be sure that when we take our random position, the flux will indeed converge to the flux according to the average, at least on the average, at least when we average in time. So we want to, for a large time, starting at any position you want, running the trajectory of the fast particle and compare it to the one to the flux coming from the invariant law, you would like this thing to converge on the average. Now, this looks like a complicated condition, but it's not hard to verify. For example, as soon as your Markov process, the one that just send one jump, the one that sends particles, as soon as the transition kernel of the particles, just takes a particle, send it to the boundary, and bring it back to the new position. This will give you a Markov process, a jump process. As soon as this jump process satisfies slight minorization condition, you have this condition here. So you don't really need to check this. So for example, this will work for the examples I mentioned to you, the Poisson kernel, the Brownian motions. They will all, this assumption looks very sophisticated, but is not difficult. The assumption which is really difficult to verify is assumption LF. The Lipschitz property of the transition of the heating kernel is not satisfied by a Poisson kernel. Poisson kernel is not Lipschitz in the domain. It's Lipschitz in the point, but it's not going to be Lipschitz in the domain. So we need to regularize a little bit if we really want to run the example with the Brownian motion. Now, under these assumptions, L and E, we fix R0 epsilon some object. Then what happened is that the limiting shape, or the RT epsilon, as you send epsilon to 0, it will converge to R of t, at least for small enough time. And small enough time is until the minimum of the density gets close to 0. If you develop areas for some reason, if R and X are such that there is a certain angle in which the density drops to 0, we have a problem, because in that direction, we will never add more small points. However, of course, if the density was assumed to begin with to be strictly positive, then you can just forget about this stopping time and have the statement that the limiting shape will converge to the solution of the ODE, which is what I mentioned to you before. And the principle of the proof of this result is, as I mentioned already, as epsilon goes to 0, the dynamic of xt epsilon is going to be near equilibrium at time scale where RT of epsilon does not have a chance to change macroscopically. Namely, what we have here is an averaging principle. The fast particle, x, is averaging, goes to the invariant measure sufficiently fast, whereas R made small changes, and because of our Lipschitz properties, the small changes did not detract us from the convergence of the fast particle to its invariant measure. And this is really the essence of the proof. Of course, there are details and they are written in the paper. Once we have an averaging principle, once we have a limiting shape, once we have a limiting evolution, we can talk about a limiting shape. Because if you notice here, what I will get this solution of the ODE, which is still a function of time. It's like a parabolic problem. Now I want to get to the elliptic problem, to a limiting shape. For that, I need some invariance. And this is an invariance assumption. And the invariance assumption says the following. Imagine that if you scale C and R, you scale R and X, you just blow up both the shape and the point. What you would like to do is that the angular behavior of your rules should not change by a blow up. right? So if you just blow everything up, you want that everything, doesn't need to be rotationally invariant, but should be scale invariant. Once you have the scale invariance, together with the averaging principle, you will have a coupling that says that the behavior of R epsilon t and X epsilon t is going to be up to a scaling the same as running at scale 1, but running for a large time. So it becomes the same running large time at speed 1 and running for a fixed time at a speed epsilon to the minus 1. That is what the scaling invariance is doing for you. And in particular, the scaling invariance holds, for example, if f is a Poisson kernel and h is the one going back by a constant, the example I gave you. And there are more examples which satisfy the scale invariance. Now, together, the coupling and the ODE, or the averaging principle, which I call hydrodynamic limit. So if we assume the result of the previous theorem and the scale invariance, that means that we have the convergence to the solution of the ODE. Then what happens if we have a function psi, which is invariant solution of the ODE, then without loss of generality, we can scale it to have a Lebesgue measure 1. And if we take our R at time 1 now, at scale 1, at time s times n, and we normalize it back by n to the minus 1 over the dimension, it will converge in a uniform norm to the function psi. That's a limiting shape theorem. In order to have the limiting shape theorem, we need, at this moment, we need to start with a R0, which is already invariant, right? So what it says is if we start at a shape which is invariant to the ODE, then the random evolution will converge to a solution of the ODE, which is going to be also invariant. We can also talk about attractivity, but this is harder to verify. Now, in the example I gave you, all the conditions, the Poisson kernel and the going back, all the conditions of the theorems are holding, both the scale invariance and the other condition, except the Lipschitz property. It is not true that the Poisson kernel satisfy a Lipschitz property when you only assume about R that it is continuous. It's not enough. You need to assume that R is slightly smoother in order to have a Lipschitz property. The Poisson kernel is losing derivatives, so you need to assume that R is slightly differentiable in order to get a certain control on the norm. And the way that this is done is simply what we do. We run or disprove the theorem for a regularized f. What we do, instead of running the Poisson kernel, given the shape, we can always smooth it a little bit at the boundary to get something which is differentiable, and then we use this differentiable guy as our new rule. And then all the mathematical assumptions are valid. In our simulations, we got a limiting shape pretty easily without that, but in the simulation, of course, the conditions I put here are not the optimal ones, are the ones we worked with. Thank you very much.
Thank you. So we can all unmute and thank Amir. And we are all open for questions. You can either ask or put in the chat.
Yeah, I had two questions. First, your assumptions L and E, do they imply that that the stationary distribution changes smoothly with the shape?
What you mean?
You had this
distribution of the particles, of the added particles.
The new R changes?
The new R, yes, yes.
We did not try to prove it. And
you don't.
Okay, we did not try to prove it, and I suspect it may not be true, or at least it may require more. What we really needed, we needed this guy to change smoothly. right? We definitely needed this guy, which appeared in the equation to change smoothly with R. So our conditions were good enough to make this guy change smoothly, but we never said anything about new R changes smoothly. We somehow they disappeared.
Okay. All right. And my second question was, do you have any examples where there is a limiting shape, but it's random?
Okay, here there won't be, because the whole thing is we are kind of averaging principle give us automatically this deterministic evolution, right? Here the first step is to move from a random evolution to a deterministic evolution. There are examples of a limiting, okay, not a limiting shape, but there are examples where there are examples of motion or random things, Earn models, for example, in one dimension, where you have a limit, but the limit is random because somehow the initial conditions are very crucial. But this is very far from these examples and very far from all the simulations of the other models where we don't know how to prove, but we suspect the same thing. In those models, presumably, you have what I said here, that a bulky shape will appear, and somehow you will have averaging. It's like essentially like a law of large numbers will emerge, so you don't have a random limit.
But maybe on say on a non-amenable for something, do you still have like large?
On a what?
Say on a non-amenable. I don't know if you do ideal A or something like that.
Yeah, on a non-amenable. Yeah. And yeah, on a non-amenable, yes. And also, I don't know if there will be a limiting shape, but if you have things coming from infinity, like in DLA, where people don't know very much or actually know almost nothing, the simulations are these are models which encourage growth. Once something builds up, it grows more like a dendrite. So you get fractal shape. And there, I don't know if you have a limiting shape, but if you would have, it will be random. If you design something looks like that coming from infinity that will have a limiting shape, it's definitely going to be random because the initial conditions are going to affect everything, because the one who leads is getting an advance. These examples are kind of models. These are all these, what we were trying to study is models with memory in Euclidean domains, so amenable, and where the growth is running from the inside. And the claim is that when the growth is running from the inside, and the rules are such that they encourage that if you are lagging behind, they kind of encourage to come there before you come to a point which is ahead, then under very general, one can say you big universality class, you will have a limiting shape. And still people don't know how to do it. This is the first model, I think, with memory, other than the uniform case, which we can actually prove anything. So it's very difficult because of on the one hand, it's all Markovian object, right? You have X and R, this is just a Markov process. So you only want to know something about law of large numbers type behavior for random, for Markov process. But this is a Markov process on a very not so nice to work with space. Your space is a space of functions plus particles, right? So it's a huge infinite dimensional space. And the particle doesn't even, definitely will not, you have a component of the Markov process which you don't even expect to converge to anything. So you have a Markov process on a huge space whose projection on some functional you expect to satisfy a law of large numbers. It's not so easy from general theory to get such behavior. So we took here a slightly different approach of separation of scales.
Mm-hmm. So can you describe the growth somehow directly as some kind of a stochastic equation that might let you get some better handle on the fluctuations and the roughness of the boundary that you get?
I think you can. I think you can do a finer analysis. We did not. I mean, you have this. Let me show you. You have the key to the analysis is this, you have this generator and the martingale decomposition of the whole thing. You can look at R and X,
Right.
the generator and da 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 da. So you have here a martingale and you have here a drift, and you have the motion of the particle, and we don't really care about that. This will have fluctuations, but they are going to be, I think, not important for you. This, I think, is what is more interesting, the fluctuation of R. In principle, you get the limit by killing this object and looking where this goes down, right? So you can subtract.
Yeah.
You can subtract the ODE, and you will get another. Now what you will need to do, you will need to analyze slightly better what this small martingale is, and I would expect it to be more or less like a white noise. And then you will have a diffusion. So I don't expect this to be impossible to do, but you will need to put probably more conditions, more restrictions, because now it's like moving from, you work on a finer scale and you will care about more stuff. But I would expect it to be Gaussian. I mean, in principle, I expect the scale to be the one that comes from as Omer mentioned, from essentially an infinite. You will have an infinite dimensional SDE, right? You will subtract the other things. You will get like a diffusion. There is the difference between. You will need to look at how this sigma, the diffusion coefficient is, and what will be the drift after you subtract the law of large numbers. May probably be zero. So you probably just get a diffusion, but the diffusion coefficient here will probably depend on the solution of the ODE, at least. Maybe even or maybe you will even have a diffusion coefficient that depend on R, on the actual fluctuation. I don't know that.
Right. Okay. So then, because the follow-up to that is whether you think you could get some limiting behavior here, which would be in the KPZ universality class. If you look at the boundary with the right scaling.
I don't know. I don't think so, because I don't see where you will get where do you get the nonlinearity term, right? I have the motion, I have the growth, but I just add bumps. So where would I see the effect that?
Right, and
maybe
I mean, it would have to come. If it would have to come from the Poisson kernel or whatever you put in place instead of the Poisson kernel. So
right.
that could give something nonlinear, I guess.
But it's not the right. It's not the right. It does not tend to.
But
maybe it tends to smooth things. I didn't try that. That's a good angle to look. We didn't try that at all. Yeah, that may be a good point. But the kind of structure we have here, if we get something that probably should converge to a KPZ, it will remain a conjecture. Because we don't have any algebra, we don't have any exact solvability whatsoever, nor any other structure that will give us, I think, any lead on proving stuff. But it will be nice to get a member of this family to have a KPZ. Maybe there is. By the way, these models look the same, or at least at the level we work, they are exactly the same in every dimension. So somehow, the fact that you have in KPZ, it's important that you have a one space, one time dimension. Here we can work with any space dimensions, and it all looks the same. So
that's a good point.
Another thing why I'm a bit suspicious about emergence of KPZ growth here.
Yes, this might happen only in 2 dimensions and might not even happen then, I agree.
Now, the one thing I would have liked to see is I would have liked to see some way to approach the original models which I spent in the beginning time to describe to you. Maybe you have noticed that I did not attack them. Originally, we wanted to solve this problem as a warm-up before we approach the problem of origin-excited random walk. So we got completely warmed up, but it did not really help us that much. And the problem is that in the examples to capturing this, it's not the lattice, I think, that is so much of an issue, but the issue is that really in all these discrete models, the main difficulty comes from the fact that that the new particle is distance, in our notation, distance epsilon, or the lattice distance 1 from the boundary. So actually the new particle is going to make a lot of localized motions, a lot of localized hits before it gets macroscopically back in. Now, you would say, but it doesn't really matter, so what? But if the boundary, that area, is locally rough, it may slow it down so much that will completely, the whole averaging principle might kind of lose at least the intuition. Now, the simulations suggest that this is not what happens, but I don't know how to prove it. It's like, it's essentially like having a priori parabolic, a priori boundary Harnack inequality for this motion before you start. But it's a very complicated motion, so I don't know how you will get a priori boundary Harnack inequality that will tell you that it really doesn't matter and that the boundary is not going to cause any trouble.
Yeah, okay, so I think some people probably need to head off, so perhaps we can thank Amir again, and if you're interested, you can stick around for some continued discussion. So thank you, Amir. And I'll stop the recording, but we can keep, you're welcome to stay.
So, yeah.